As Malte mentioned, my topic for this presentation is machine learning algorithms. How do you choose the correct algorithm for your problem? And the focus group is those who have not had a lot of experience with machine learning and AI. Those with a lot of machine learning will probably know most of this, but for the rest, it could be a really good introduction. Because when I started with machine learning, I felt a bit like this. I felt like machine learning is a big black box of magic that I don't really understand. Some of the algorithms make kind of sense, but what's the difference between them? Why does some work on some problems and others on others? I didn't really have any clue. And to be honest, I think that's fair because there's a lot of different algorithms that's pretty recognized. And this is a short list. So you have a lot of options when it comes to choosing an algorithm. And before we go into the big stuff, I just want to have a quick disclaimer. I'm no universal expert on machine learning algorithms. I'm not a guru who can tell you that's the perfect algorithm for that problem. This presentation is more a summary of what I have in my head and try to structure that in a sensible way. So don't kill me if I say anything stupid. So in my opinion, it's 4 categories which you can have machine learning problems in. Some will say it's 3, but I say it's 4. And that's supervised, unsupervised, semi-supervised, and reinforcement learning. Before I get going into them, I have one quick slide to describe an important word for those who might not know it, and that is labels. I'm going to use that word a lot, so if you don't know it, it's going to be a boring presentation, but label data is a group of samples that's been tagged with one or more labels. For an example, if you want a machine learning algorithm to estimate the value of a car, it has a lot of features: the age, the make, the mark, the mileage. And the value you put on a car, that's a label. Everybody got that? Cool. All right, so supervised learning. First, I'm going to start with the definition. Supervised learning is the machine learning task of inferring a function from labeled training data. And the only 2 words you really need from that sentence is labeled training data. That was 3 words, whatever. So supervised learning, you have a training data that consists of a set of training examples. And the idea is to find the most optimal model parameters to predict unknown labels on other objects. And this can be divided into 2 different categories. The easiest one, in many people's opinion, is regression. This is where you have a label of a real numeric value. For instance, dollars, weight, height, and the value of the car, which we previously spoke of. The other class is called classification. This is if you have the label from the limited number of values where the values can be unordered, then it's classification. So this can be colors, disease, no disease, spam, no spam, a lot of different categories. And there are so many algorithms that's really great for supervised learning, but I'm just going to mention three of them because these are good starting points. And I'm going to talk more about these later, so I'm not going to go into detail. Unsupervised learning is where you have a task of inferring a function to describe hidden structures from unlabeled data. So like in the supervised set, unlabeled is the key for unsupervised. So unsupervised learning is where you have input data, but no corresponding output variables. And the goal for unsupervised learning is to model the underlying structure or distribution of the data in order to learn more about it. And you can claim that it's no really correct model for unsupervised learning. The algorithms are left to their own to discover and to present the interesting structures of the data. This can also be divided into 2 categories. You have clustering, where you want to discover the inherent groupings of the data. For instance, grouping customers by the purchasing behavior. And the other one is association. An association rule wants to discover large portions of your data, like people who bought X, they usually buy Y. And Netflix has a video recommendation system. I'm pretty sure most of you have seen that. It consists of a lot of layers of different AI, but this is the one that's most intuitive if you wanted to design something like that yourself. I also put down a couple of examples for starting algorithms for unsupervised as well. There's one that's called k-means, which is really great and not that difficult for clustering problems. And something called a priori algorithm for association rule learning problems. Third one, halfway there, semi-supervised learning. This is problems where you have a large amount of input data and only some of the data is labeled. So obviously this falls kind of like between supervised and unsupervised, kind of comes from the name, I guess, where you have partially labeled data. And in fact, there's a lot of real-world machine learning problems that falls into this area. This is because it can make it really expensive and time-consuming to label the data. You might need experts, for instance, to label the data, whereas unlabeled data is pretty cheap and easy to get a lot of. An example is a photo archive where you have some of the images labeled. This is a dog, that's a cat, that's a person, but the majority is unlabeled. So I'll go on to 3 of the 4 different categories so far, but a short summary because they are so equal. So supervised learning, you have labeled data, and the algorithm tries to learn to predict the output from the input data. In the unsupervised case, you have unlabeled data, and it learns the inherent structure of your data. And semi-supervised is a mixture of both, best of both worlds. Final category is reinforcement learning. Reinforcement learning is an area of machine learning concerned with how software agents ought to take actions in an environment as to maximize some notion of cumulative reward. That sounds a bit Greek sometimes, but it's different from the other supervised learning situations. You don't have any labeled or unlabeled data. You have no training set. In fact, like you can see from this figure, you have a really amazing robot. It's called an agent. He's going to take some sort of action, do something in an environment, for instance, the globe. And based on his actions, the environment will either punish him or reward him, depending on how you implement it. And after that, you're in a new state, and that process starts over again. So differently, imagine if you yourself are the super awesome robot, and you're in some strange place you've never been before. You have no idea what's going on, so you just do some activity because you don't know what's going on. And then you get the rewards from the environment based on what you do. And after some time, each action, your behavior is getting more complex and problem where you can have reinforcement learning. Out of battery?
Yes.
Some other examples is chess and Go. I think it's been mentioned here before, but last year, AlphaGo, Google's DeepMind, managed to beat one of the best players in Go, which is highly more complex than chess. So that was a big step towards machine learning, especially because it wasn't influenced by humans. It managed to do some actions that we haven't seen before. It learned by itself. So we as humans can now learn from the machine learning algorithms, which is pretty cool. And also, last year was a great year for reinforcement learning because OpenAI managed to create an algorithm. I don't need this anymore. Create an algorithm to play Dota 2, which is a real-time game. That's completely different than the other games because you don't have time to think, you just need to react. But they managed to create a neural network that played against itself and became better than all of the players it played against. Any questions on the 4 different categories before I move on to some of the algorithms? All right, everybody got everything. That's impressive. All right, first algorithm is maybe one of the simplest algorithms in machine learning. This is a great place to start if you've never done it before, given that your problem is in the supervised learning regression area. Basically, you're gonna have a lot of features and labels, and you're going to try to find the optimal weights and bias to reduce some loss function. This is taken from mathematics to make a straight line. Some examples here is like this one. You try to map the age of youth or children or babies towards some height. You can do the same for countries versus height, or a lot of things where you want to map two variables against each other. Decision trees are maybe one of the most intuitive machine learning algorithms. This is the first one I understood what was going on. It can be used both for classification and regression within the supervised domain. You have, is it this one? There you go. So you have these nodes, and then every node you try to maximize some functional based on your features and your labels. And you make that procedure recursively through all the way down the tree. And the height of stopping criteria might vary from one leaf, like here, to the height of the tree, like these ones. So here's a great example you should show all of your friends who are unsure if they should work for Knowit or not. First of all, the question is going to be, do you pay enough? Yes, of course we do. Do you have to commute a long way? No, because you live in Oslo. Great. Do you have free coffee? Yes, we do. So they should start working here. Show that. It's easy. My favorite algorithm, because this is the one I've worked the most with, is called support vector machine. It's the final algorithm I'm going to talk about from the supervised domain. It can be used for both classification and regression, but it's mostly used for classification. What you do is that you plot values as a point in an n-dimensional space, where n is the number of features that you're dealing with. And then you perform classification by finding the hyperplane, which is the one here in the middle. That separates the two classes. And you also have support vectors, which is these lines, that defines the area in order to get classified as one of the areas. So with this, the great thing about support vector machine is that if you have a complex case where you don't really know, it's kind of like in the middle of the boundaries here, then you can say, we don't know. But everything from here and down, we're pretty sure is in this category or equal here. So that's the one we used, as I talked about once before in this fall, for Oslo City, in determining how, if a parking fine should be accepted or rejected. Then we would say if it's an easy case, yeah, we know what's going on. But if it's difficult, we say we're not sure. K-means is, as I said earlier, a great algorithm for unsupervised clustering problems. I think this GIF is better at explaining what's going on than I am. But what you do is that you divide all the data into K clusters, where K is your number of definition. And then it will select K random points among all the data points and name them the center of cluster. And then the cluster becomes all those points which is closest to that center. A great example where this would be useful is if you have a pizza chain. Let's say Peppers Pizza wanted to go to Sweden, if they're not there already, and develop new restaurants in Stockholm. Then they can take a lot of variables, for instance, the population density around the city and different pizza places, traffic around the area, in order to find the optimal placement for the restaurants. That's maybe our next customer, right? And you can't have a talk about machine learning algorithms without touching at least slightly within neural networks. And this is way too big for me to talk about here, but I'm just going to say that neural networks is great for super complex unsupervised and reinforcement problems, also for other, but especially when the problem becomes too complex for using other algorithms. And that applies especially to text analytics, sequences, images, a lot of them. But for me, I'm still here where I can understand that, okay, I do something to some algorithm I'm slightly understand, and that determines, while deep learning is just a big black box of something. Don't start there if you've never done machine learning before. I wish I could mention a lot more of the algorithms, but that would be boring and you wouldn't remember anything. So I've just listed 4 honorable mentions, which should have been given the time to be here, but they have not. For instance, naive Bayes, it works on the assumption that every feature is independent of another feature. Even though they are related, it's going to assume they're not, which can be a really effective way, at least in some cases, to do cement analytics, text analytics. It's really compute effective and it's rather easy to understand how the mathematics behind it works. And random forest is just a combination of many decision trees, which is also pretty awesome. Do we have any questions? I once heard that if you have no questions, nobody understands what you talk about. All right, then that's all for me. Thanks.